大家好，欢迎收看 Light 人物访谈的海外系列节目，我是你们的老朋友 Light 科学编辑袁静泽。今天我们来到了意大利国家研究委员会应用科学与智能系统研究所，并非常荣幸地邀请到了 Pietro Ferraro 教授来同我们分享他们团队最新的研究进展以及未来的发展规划。Ferraro 教授团队的研究内容覆盖物理学、化学、生物学等多领域交叉学科。在过去30多年的科研工作当中，该团队深耕数字全息成像领域，并与同行一道完善并健全了该项技术的基本理论，提出了多项次时代的数字全息成像新方法。作为团队领导人，Ferraro 教授是应用科学与智能系统研究所的前任所长以及现任研究主任，并在衍射光学领域和成像光学领域都有着突出且重要的贡献。好，那接下来就欢迎观众朋友们同我们一同走进 Pietro Ferraro 教授以及他的科研团队。
Holography has been invented by Dennis Gabor, that was awarded by Nobel Prize in Physics about holography. The true revolution about digital holography occurs in the 19, which CCD, CMOS with high resolution solid-state sensors were available. With the advent of digital holography, instead many steps forward were made in developing holography, thanks to the powerfulness of a personal computer, powerfulness of software that allows to processing, and the main concept about digital holography lies in the fact that you can manage numerically the complex wavefront scattered by the object. This makes a big difference in respect to the past concept of holography for digital display. You can appreciate the three-dimensionality only by looking to the hologram and looking in the window to appreciate the parallax in image in 3D. Instead, by means of digital holography, you can manage the complex wavefront. You can retrieve and managing the numerical data about hologram, and this opened a lot of important future for the development of holography in the next step. In fact, there is a possibility to make correction of aberration, imaging at different depths. And I believe that holography has still a bright future, as not discovered yet. And I think one of the most two important fields for the future of digital holography, for sure, clinical application for single cell analysis and diagnostics. And the other one is for monitoring environmental pollution. So, optofluidics is a combination between optics and fluidics. What is very important for digital holography in future perspective is the possibility to make a combination between the capability of imaging, thanks to the optics technology, and combined with the microfluidic technology. Because combining both in a single compact device can be the solution for many problems of humankind, regarding the health of humans, but also the environment protections. So essentially, what we are trying to do is combine a holographic microscope with microfluidic channels and circuits in which there are flowing, for example, red blood cells or white blood cells or any kind of cell in body fluids, taken from body fluids. And by means of holography, we are capable to detect, for example, sick cell flowing inside the channel. This is very important for early diagnosis for human. It's very important to develop very compact system that can provide simple diagnosis in remote locations, and this will be a revolution if we are able to develop the so-called lab-on-a-chip device. So we are taking essentially for the future development of digital holography by optofluidic, we are taking benefit of different important stuff that have been developed in the last decades. Compact light sources, compact lasers, compact LED sources, compact and very cheap and high performance imaging device like CCD or CC sensors, and the other side microfluidic technology combined with nanotechnology and nanofabrication. Combined all together, I think we will have a big benefit for humankind. This technology can be used, for example, for human health, for early diagnosis of disease and so on. But of course, on this concept is based on single cell analysis, for example, for personalized medicine. But to do that, of course, making a diagnosis based on imaging technology, you need to acquire many images. That means with high resolution imaging sensor, that means you have a big data to manage different things. And so the other point is that it's necessary to make assessment of very teeny difference between sick cells and healthy cells. And so this cannot be done by human brain, by single observation of the single scientist or single clinicians that is able to discerning and to searching for sick cells. So artificial intelligence and deep learning or machine learning can be very helpful in changing this kind of a technology, so making possible this diagnosis very rapidly and very reliable by taking account any teeny difference between different cells and just to discover new biomarkers to identify old diseases or new disease. So the enforcement of digital holography, compact microscope for lab-on-a-chip application, together joined with artificial intelligence, for sure will fuel the future application and for medical application, household industries, environment pollution, and many other kind of application by managing and processing and allowing diagnosis for clinicians in a very rapid, affordable way. We are trying to find a new solution for optical diagnosis by means of digital holography, and specifically we are trying to make high throughput digital holography system for analysis of single cell. So one of the most important topics that we are working on now is on the possibility to search and identify circulating tumor cells in human blood. That will be a very important result if we will achieve to get this kind of result, because usually in a drop of human blood, in case of presence of circulating tumor cells, there are very few tumor cells. So this means that you have to analyze and processing a huge amount of the cells when you analyze just a single drop of blood. And so our aim now is to try to develop a reliable system that is capable to make a diagnosis by discovering new biomarkers, by analyzing 3D structures of the cells. So essentially different from, for example, for fluorescent microscopy. We are trying to use holography because it's able to give you quantitative measurement or physical measurement about the cells, and by means of in-flow tomography we are able to retrieve the three-dimensional structures of each single cells. And now what we believe is that we can find new biomarkers just by looking at any teeny element of a three-dimensional structure of a single cell. So this will be our main aim in this moment. We have several projects working on this, and so again in this case we are using, we are trying to develop artificial intelligence in support of digital holography for speed up the analysis of a single cell analysis. Here in my group, we have available 6 optics laboratory and 3 laboratory of support, one in material science, another one in biology, and another one about mechanical workshop. Essentially, in different labs, we have a multitude of optical tables equipped with different optical setup, mainly based on interferometric or digital holography, and each one setup is arranged to develop new application in different fields. Now you will see explanation and illustration different optical setup for different applications by each one of the members of my team here at ISASI.
My research activity is mainly focused on new technique for microfabrication. In particular, I work on innovative inkjet printing, direct writing and self-assembling approach for the fabrication of lenses or microstructure for lab-on-chip devices. This lab-on-chip could find application mainly in the healthcare system, but we are also working on the functionalization of microstructure for photonics devices. Our technology are mainly based on the use of the pyroelectrodynamic effect that allows us to control and manipulate liquid and also high viscous polymer. We didn't use nozzle, but we start directly from a liquid droplet so that we can work on different kind of material and achieve a very high resolution in the printing process, produce different microstructure, create some channels so that we can design and then realize lamp chip of different dimension with different geometries or characteristics as a function of the final application. And we can also functionalize this system by the direct writing approach, and so printing directly onto this chip some lenses with different optical characteristics. We can control the optical structure of these lenses. Using our technology, we are able to control and manipulate the material and create different three-dimensional structure. And we can also achieve high resolution in controlling the fabrication of microneedles that could be used for guiding light. Our advantage is that we can work on biocompatible material, so all our system could be used as a biomedical element and also could be directly integrated with different lab-on-chip devices. Working on a polymer that is mainly used for biomedical application like the PLGA, we avoid all the problem of cross-contamination. One of the real advantages of this process is that we are completely contact-free. We use this pyroelectric effect for controlling its deformation and the printing process, so we completely avoid all the problem of cross-contamination.
My work is framed within the topic of computational microscopy. One of our main activities is the single cell analysis through holographic microscopy in flow cytometry conditions. One of the main applications is the cancer cell detection. Essentially, we are looking to search to catch these cells in the bloodstream, trying to realize the liquid biopsy paradigm, and this is obtained through advanced image processing techniques. Essentially, we record the digital holograms of flowing cells, and after an holographic reconstruction process, we are able to obtain phase contrast images of these cells, but also we can obtain a three-dimensional refractive index mapping of these through phase contrast tomography reconstruction. And the main goal is to obtain a synthetic representation of these cells, of all the cells that flow in our system, with the aim to discriminate some population, and in particular cancer cell. This is obtained through managing the holographic data by using, for example, morphological features, phase features, or other features that are distinctive respect to that class that you want to detect. For example, in the case of tomography, we are looking to inner structure, to subcellular structure related to the morphology of these cells, and is obtained, for example, in the case of phase contrast tomography, in which we are catching, for example, to the nucleus, to the other organs that are morphologically related to the state of the cell, so in that case the cancer syndromes. Okay? New research are based on the possibility to decouple the information of the subcellular structure through, for example, advanced image processing based on the Nike polynomials and other processing-based application like this. Of course, one of the core of this activity is the artificial intelligence, in which we use these features to train a classifier that is able to distinguish between different classes.
I mainly work on digital holography and application in microscopy. Especially in the last years, I worked a lot on application, on health application for life science, but also for the detection of pollutant into water. And in this field, we demonstrated that it's possible to detect microplastics and macroplastic fibers into the water, and also it's possible to distinguish between different kinds of plastics and fibers, synthetic and natural fibers. The technology has been developed integrating digital holography, polarization sensitive digital holography, and microfluidics. So the great challenge is to distinguish these materials when they are flowing into microfluidic circuit. And this is for two reasons. The first one is that we can have a high throughput because we can manage many liters of liquid passing into the system, but also our technology is label free, so we don't need to manage the samples with chemicals or other destructive elements, and is completely all optical and label free. So we are able to distinguish by the birefringence of these materials, the presence inside the samples, and also to distinguish different kinds of plastics. The challenge for the future is to analyze much more complex samples and identify different types of plastics, also of different shapes, and also when they are embedded in, for example, inorganic samples.
One of the activities that we carry out in this lab that I'm going to show you is related to the possibility to bring all of the functions of a holographic microscope out of the optical lab. The motivation behind this work is to allow that some of the diagnostic possibilities can be brought to everyone in the absence of facilities, in the absence of an equipment for this. In the next future, instead of having a lot of subjects doing diagnostic screening in diagnostic centers in the hospitals, some of the devices that we are trying to develop are devoted to improve the compactness and robustness of all of these microscopes. So a few years ago, we developed the technology that we call holographic microscope slide. The idea is to merge microfluidic technology, lab-on-a-chip technology, and holographic flow cytometers to take a plain fluidic chip like this one, which is made of plastic and is made of polymer, is a very cheap lab-on-a-chip device, and to functionalize it, so to put optics on the top of it, to turn this very simple device into a holographic microscope that is all planar, all made on chip. Instead of having an entire interferometer, we have one single beam impinging on the chip. So this makes everything very, very simple. So at the end of the day, we have a planar wavefront division interferometer, which is very, very stable against vibration. So everyone can take it, let the sample flow. So for example, blood drop flow inside it, and image every single cell in a quantitative and label-free way. So there is no marker needed. So there is the complete absence of facilities to have reagents that have to mark the sample and stain the sample. Possible application of this kind of technology are related, for example, to make blood screening, blood testing, and of course we put intelligence in these microscopes. So once we acquire the data can be processed and data can be classified. So all of the population can be classified using one of the existing machine learning frameworks that everyone can use. So the idea is to make all of this field more accessible to everyone.
So setting up a productive team of research is not an easy task. I think there are three main important value that has been built up in a research team, like in our team. The first one is they should learn the attitude to work together, just to exchange, not to be jealous, but just to exchange information. The second one is to be open to the others. That means that usually what we do is there are teams that sometimes are focused on one project and teams focus on a different project. But can happen that if we have a discussion with the different groups, and the people can also change the team or also add his personal contribution to the other team if he has an idea. It doesn't matter. We don't put barriers between different groups or subgroups in my wide research group about digital holography and material science and so on, independently from the second aspect is related instead to the interdisciplinarity. So I'm trying to hiring different people, smart people possibly, that came in with different expertise or from having different backgrounds. So we have physicists, telecommunication engineering, informatics, biologists and things. And what we do is to try to conceive new ideas and new research just by discussing all the people together, not to taking separate biologists by engineers and so on. So this is one of the secrets I think in my group in which we are pushing a lot toward transdisciplinary research in which each one can give his own idea, his own contribution just to develop a completely new idea. So I'm pushing for creativity and so I stimulate and I encourage them to be creative.